I was talking about how you guys can't even hear me yet. It was cold this morning. It's hot today, and it's going to snow on Saturday. Onliners, what do you think about the snow? You guys got this. It's crazy hair. Not going to happen. Michelle is naysaying the snow. No extra credit for that. I love snow. You guys know where I'm from, right? I'm not wearing it today. No one knows where I'm from, where I was born. New York, from New York. I'm a New Yorker. I opened a door for an old lady one time. She's like, "Thank you. You're a nice, fine, young Southern gentleman." And I was like, "Thank you." "No, I'm not." Slam the door in her face. "Take that. I'll show you courtesy." I just smiled, of course. What? To the what? I don't know what the what is to. I guess I can join as pod user, and then I can screen share as pod user. I guess I can. Maybe I've never even had to log in as myself on this. It's probably gonna be like, oh, is it gonna say like someone's requesting access? Look at that, we're all logged in. It's pod user. It's kind of cool. I wish we could have these two things going. It's pretty neat. Like, I've actually had ideas with this. I'm gonna throw this out here. We're 2 minutes before class right now. We're actually like early ones. Usually start like right at 5:05, like 5:05 webcams turning on and all that stuff. You know what I mean? Like, you guys feel like class starts on time? I feel like it's maybe like a minute or two late sometimes, right? Like, that's the most, but we're pretty on time. Onliners, what does onliners think about the on time starts? Usually I give the overview of what's going on. I mean, you can't start class at like, okay, let's start learning. It's like, usually talk about, oh, glad. Michelle, okay, Michelle, you get extra credit for that. You're the onliner talking right now. I like it. Thank you, Michelle. So she says, woo. But I feel like we do start on time, and that's our point. So if you ever watch one of these YouTube videos and you're like, wow, he's rambling, it might be because we had 2 extra minutes and we're in that right now. So let me ask you this. I've had ideas, and frankly, I've got like, you guys ever see those Kindle Fire tablets? They're like $30. I mean, they're super cheap. And you get the ones with ads, because if you buy the ones without ads, they're like $60. So you always have to like flip past an ad every time you open it up. But if I had one of those in here, I could have it being charged in the wall, and I could have it like facing you. And I don't know if they have cameras. Does it have a camera? It probably doesn't. It does? Really? So, but I wonder which way the camera, does the camera face you?
Yes, the camera's on.
We could have it. What would you guys think if in the classroom there were seats you could sit in, and then like if you had a question in class, I could be like, oh, so-and-so has a question. Okay, go ahead. And then like you'd be talking. Would you guys like, you know, you don't want me on camera, right? I've always thought I give you guys the ideas, and you guys are like, no, don't do that. No one wants to be on camera but you, Brian. I like it this way. Don't make changes, Brian. But I've always thought that'd be kind of cool. And like it's like, oh, like it's basically like you're like in class. I'll tell you my last idea. This I don't want to say this idea already hasn't won the approval of my girlfriend. But I'm pinning the videos right now so we can get those pinned. Make sure the lecture's doing right. Here's my other idea. You guys ever see like the VR tech that's out right now where you put on like the Samsung Galaxy Gear, you know what I'm talking about? Or you put on like the Vive or the Oculus Rift or all that stuff. Well, so if you have like an iPhone, you can get those things and just have the iPhone in front of your face like this and just be watching. And when you move your head, it moves you around the VR world. Well, what if we had in the middle of the classroom, or like not where, like maybe where you're sitting, like I put the thing here, but where you're sitting, like you're the thing. And so you could look at me, or you could look at the screen to see like the notes. No, but the problem is you're not gonna be able to look down and write stuff. That's the problem. Would that be cool?
Yes,
That'd be cool, right? I'd like to be like the first class to do that, like UT first class broadcasted online VR. So like we'd have like a 3D camera here, and you could watch it live in 3D, and we'd be broadcasting a 3D event where you could put on your Galaxy Gear or whatever and like do a 3D live class. You guys think that'd be cool, onliners? No, how's that idea pass? Is it gimmicky? UT plops down $100,000 for a 3D camera. I don't know how much those things cost. Do it. Is it to do the 3D thing? So does it have like multiple cameras where they then splice together the image and you basically switching between so it's like maybe 3 cameras that are getting enough to make a 360, right? And then it's just feeding, so it's the software doing it mainly. It's 3 feeds that actually when you go between, it's splicing the feeds. Understandable. How expensive is that tech? We only get the F from online. Huh? Streaming good quality is the other, yeah. You know. Something to think about, kind of the future, who knows? Because I mean, imagine if you could take any class. Can we get I hope back? IHOP. That was underneath, yeah. IHOP, that was underneath the presidential. No one went there. I liked it though. They were not a top quality IHOP. Oh, I'm so glad Sequoia likes it this way. Sequoia and Garrett, all of you, extra credit, even for the IHOP back. I'm glad you guys like it. I'm glad you like it, Sequoia. I'm glad you guys like it. I'm always like trying to improve. I'm glad you tell me when you don't like the idea. You don't want a bunch of yes men, yes women, be like, that's great, Brian. But if you guys like the way we're doing it now, and a lot of people have told me they like this, the people who attend online like it because it's basically like you're right here. And I've always been told that they like this format. We used to do it differently, but when I'm like looking at them, I'm actually reading your comments on the screen. So I'm actually seeing everything right here because the camera is right there. So when I'm looking at you and talking to you, and I think the onliners like that. So good stuff, onliners, and in-classers. You guys know when I'm talking to you, obviously. But I'm glad you guys like it. Let's get to some lecturing. It's 5:08. We only talked about that for 3 minutes. Just wanted to bounce those ideas off you. If you ever have any ideas, talk to me. I'm always thinking of how do I make this better? Because I want to say this. The first time I taught this class, it was not like this. It was not like, okay, here's what we're doing. Boom, boom, boom. It wasn't disorganized, but this has grown. But you don't always need to change. You maybe figure out what works and you keep doing it. I like change though. Well, I like change when I do stuff like this. I could eat the same thing every day for a year probably. Pancakes and eggs. Right, Garrett? Garrett, you with me on that one? Garrett and I are just gonna go to IHOP. Pancakes and eggs. Maybe some sausage. What is that? Garrett's down for that, man. What is the one sausage thing that comes in the green box? It's vegetarian. Does anyone know what I'm talking about? Oh, I know the name of it now. Vegetarian sausage in the green box. There's my New York accent sausage. I'll give you extra credit if you know the name of it. I remembered it. I only got like 5 seconds. Nate and Mackenzie, some extra credit. Both to Nate and Mackenzie. It's Morningstar. Morningstar makes some pretty good stuff. I couldn't think of it, and I remembered it before you guys. So Garrett, some extra credit. Why not? What's a good breakfast place? Where do we need to go? Where? The Egg and I, or not that great. Don't where? Oh, the French Market. Go to the creperie. Go to the creperie. Waffle House.
Yeah.
There you go. That's what they're thinking in class. Extra credit to both of you from breakfast places. Okay. How about we talk some stats? Let's talk some stats. We got here sampling distributions. So bonefish brunch, endless mimosas. We've lost the class. We've lost the class. Everyone's going over there now. Are you guys ready? This is like stat space right here. We got stat space now. So let's talk about, this is maybe one of the harder chapters. Garrett's out. Here we go with one of the harder chapters, so let's all concentrate. Let's start from the very beginning. Very good place to start. We're going to talk about a random variable right here. A random event X. It sounds like, what are you talking about here, Brian? But it's going to make sense in half a second right here, because we're going to talk about discrete random variables. Discrete random variables are going to be denoted as the lowercase letter x, and we're going to look at them right here, and we're going to look at events happening. And frankly, I think the easiest way to look at it is when we actually get to this right here. Let's decode this and make sense of this. When you see this right here, this is discrete event x. And what does a discrete event mean? Do you guys remember back from when we used to talk about discrete or continuous? Discrete means what? Look at it. Whole numbers, Sequoia X credit. Discrete means whole numbers. We have examples of discrete events such as like shark attacks or points in a soccer game or subs sold at Subway. We're not going to do like half subs. You just buy a sub or not buy a sub. How many subs did we sell today? You could ask how many were footlongs or 6 inches, but you would just ask things like, how many subs did we sell? And you would give a number. How many cats do you own? If someone says 2.2, you get a little scared, right? You're like, what are you doing? A little confused there. So discrete random events are like when you go out and play your soccer game, you could score 0 points, 1 point, 2 point, 3 points, 4 points. Does that make sense? Discrete random events. But would you agree with me that there is likelihoods for these? There is likelihoods of things to occur, especially when it's limited. Like when you flip a coin 5 times. We could talk about the discrete random event of the number of heads you get. Does that make sense? The discrete random event of the number of heads you get. So that's what this is showing us right here. This is a question that has killed people on exams. I think we did this verbatim from the slides one time, and it almost caused a mutiny in the classroom. I am not kidding. Someone yelled out, excuse my French, they said, "This is Brian Stevens," but they didn't say Brian Stevens. You get what I'm saying, right? They said, "This is Brian Stevens." And the instructor was like, "What?" They're like, "That's not Brian Stevens." Oh, if it had been, see, like, if it's your first time teaching, or if I don't know what I would do if that was my first semester. If it was now and someone did that, I'd be like, "You have to come here with me right now." I would immediately like address it. I'd be like, "We're walking out of this classroom." I'd say to my TA, Anton, I'd be like, "You're in charge." I'd be like, "You're coming with me. Don't do that. Don't disrupt my exam. Say something. If you have to talk to me, talk to me." I like having done this for a while because you know how to handle things. Yeah. But do what? They did during the exam. Even during the classroom, I'd be like, "We need to talk outside. We need to talk about the conduct." And if they didn't want to talk, then they'd be talking to someone higher up than me about it. And if they weren't cordial with me outside, they'd be talking to someone higher up than to me. You usually try to let things slide. You usually try to be like, "Okay, we had an outburst, let's calm down." You know what I mean? Conflict resolution. So let's not have that occur and learn this. So here we are. You ready? What do we have going on right here? We are going to take a coin. And what are we going to do to that coin? I have no coins today. We're going to flip it, right? Do you see me flipping the imaginary coin? Every time I flip the imaginary coin, it's going to come up heads or tails. How many times am I going to flip that coin? 5 times. What are the things that can occur? I could get.
No heads.
You got it. Points for the unison. 1 head, 2 heads, 3 heads, 4 heads, 5 heads. What do you think is the most likely event? 2 or, does that make sense? If you flip a coin 5 times, the most likely things to occur is that you'll get 2 or 3 heads. The least likely things to occur, explained to me in words, would be blank or blank. Perfect, exactly. All heads, no heads, 5 heads, 0 heads. Those are the least likely. Imagine if I flipped it 100 times. It'd be very unlikely that I'd get 100 heads or 0 heads. It'd probably be likely around 50, which is ironically the proportion of the coin, which is what we see in the law of large numbers. So what we see in this table is a probability mass function. So we have a PMF. It's a probability mass function. That's what this stands for. This is what everyone's like, "We never saw that." And you only see it once. But this is important to when we talk about probability. Because what's the probability of getting 5 heads in a row on a fair coin? Well, that's what it is here. You're right. Probability mass function. How about 0.5 times 0.5 times 0.5 times 0.5 times 0.5? Well, explain to me why I just did all that. So explain to me in words what happened when I flipped that coin. On the first flip? Correct, because it's 0. I got tails, then the second one. And what word are you going to join between each one? And is the coin flip independent? Does that coin care from coin flip to coin flip what I flipped? So each coin flip is independent, so we can multiply them together. And look, besides the decimal places being annotated, we get that number. And they might say to me, Brian, why is this one this way? Well, still, if I get tails, what's the probability of tails? 0.5, and then I get heads, 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 heads. What is that mathematically equal to? These are the harder questions that will kill people. Tails, and then heads again is still equal to. So why is the probability not the same? Because we could get tails, tails, heads, 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 or we could get, I'm reversing it, it's supposed to be heads. We get one heads, right? This is one heads. Do you agree with me? If we flip a coin 5 times, these are all the ways we could get one heads. So how many ways are there? 5 ways. So couldn't you just say it could happen this way, or this way, or this way, or this way, or this way? So what can I do with those? Say it. Add them. When I said or, because think about it. If I have something that occurs and they all have the same probability, these would all have the same mathematical probability, right? Because everyone see that. And then when I'm saying or this way, because could the sequence be this or this? Can it be this and this? Those events are what of each other? They're very dependent. They're disjoint, because if the sequence is this, can it be this? So they're disjoint. The sequence being this depends on it being this. Disjoint events are dependent of the other event. So we see that all these are disjoint, right? Like one sequence being our sequence means another sequence was not our sequence. Does that make sense? And so I can add them up. Would you agree they all have the same mathematical probability of 0.5 to the 5th power? And then if you add something up 5 times, it's the same as multiplying it by, and guess what that rounds to? 16. Oh, my mind blown. Now the other ones are a little bit more complicated when you look at the ways in which you could get 2 heads. I could show you it. You just have to list all the sequences. There's a way to do it. The mathematical computation is literally 5 factorial. I don't like it then. 5 factorial over 3 factorial, 2 factorial. We're not going to get into that. I just wanted to show you where these numbers come from. This is the probability you get what? Explain to me what this is showing in this table. 1 head, probability of 1 head. How did I get what, Sequoia? Ask again, Sequoia. Sequoia's a question. 0.16. Let me show again. Let me go back to this. Each of these sequences has a probability. I think it's this. Oops. So each of these sequences has a probability of this, Sequoia. And so the ways in which we can get 1 heads is this way, or this way, or this way, or this way, or this way. And so we could add this up 5 times, but that is the same as taking that and multiplying it by 5, because we're adding it up 5 times. Because each of these is mathematically identical to 0.5 to the 5th power, which equals that. And so if we were to add them up, because they're all disjoint events, then we would get 0.15625, which rounds to 16. We're rounding it in this case. Does that make sense? Ask question. The reason for that is what this is equal to right here. The reason for this number is this and this are the same thing, because all of these sequences are 0.5 to the 5th power. Unless I've done my math wrong, that should be correct. 50, 25, 12.5, 6.25, 3.125. That's correct. 0.5, why is it 0.5 right here? Probability 50% of heads. Why did we do 5? 5 different coin flips. We're flipping the coin 5 times. Yes, that's exactly right. Sequoia really brought it home. We used the multiplication rule to find the probability of the sequence, like when we said this happened, and then this happened, and then this happened. Then we use the addition rule to add up the sequences that could occur, because only one sequence can occur, right? Which means all sequences are what of each other? Disjoint. They're disconnected, disjoint, they're mutually exclusive. And since they're disjoint, that means we can add them. And we because that's where people get confused. When I multiply by 5, I'm actually just adding it 5 times. So it looks like, so repeat what I said. When we multiply together 0.5 times 0.5 times 0.5 times 0.5, we're saying I flipped the coin and it came out heads and then tails and then tails and then tails. So that's the multiplication rule with independent trials of an event. And then we have, well, the sequences that could have occurred are this sequence or this sequence or this sequence or this or this. And we acknowledge that only one of these can occur. If this sequence occurred, these sequences did not occur. So they're all disjoint of each other. Since they are disjoint, we can add this up 5 times, and adding it up 5 times is the same as multiplying it by 5. So we just did that to do it quicker. Instead of add, we multiply by 5. Does that make sense? This is a really good example question which covers a review of what we've done. That's why I like it. There's a little bit more review here too, because we're going to use what we've learned. I think Sequoia has it. I'll see if she has anything else. Great questions. I'm sure a lot of people watching this are probably like, yes, thank you for the questions. Now, why is this a valid PMF? What laws? Okay, if you have more questions, feel free to ask. What laws of probability have we learned that might have anything to do with this being a valid PMF? Well, laws of probabilities. There is a law of large numbers that we use with probabilities to say that in the long run, with a lot of trials, we should observe the true probability. But what do you notice about each of these probabilities? Each of these probabilities is, think about, why would this be valid? Like a valid PMF, which would be all the probabilities that mass up, they mass up to 1. This is a probability mass function. All the probabilities should mass up to 1. And if we look at this right here, 3 plus 6 plus 1 is 10. 10 plus 10 is 20. 20 plus 30 is 50. I'm doing the math a little bit weird here. I'm breaking it down to parts, but it does add up to 100. Beyond that, well, what if I put in a negative 0.05 and a positive 0.05? That would add up to 100, right? So that'd probably be valid if I put negative 0.05 and positive 0.05 at the end here. Would that be valid still? Why? Why is that? Well, come on. You can't have negative probabilities. So valid PMFs have 2 conditions. I like for us to think it out first, because then if you've thought it out, you've said it, you're like, okay, wait. All of those probabilities, we got this weird notation right here, that the probability of all of the discrete events add up to 1. And that's how it reads. The sum for the probability of all the discrete events adds up to 1. The sum for the probability of all the discrete events adds up to 1. Each individual probability, and technically, I guess if they have to be greater than or equal to 0, then they couldn't be greater than 1. Because if they're going to sum up to 1 to balance out anything over 1, you would need a negative. Does that make sense? So you could use that rule. I like to say they all have to be between 0 and 1, because we've learned that probabilities are between 0 and 1. And then the set, and think about a probability mass function is really just like a set of all events, the set of all discrete events and their probabilities and the mass of them. So you can just write out a table. A probability mass function is a table where you will look at the discrete event x right here, and then the probability for each of those discrete events. My brother plans to have 5 kids. So all this talking about Darren. What is the most likely amount of boys he will have if he has 5 kids? And this is, then X is the number of boys. 2 or 3. I'm going to flip a coin every night to figure out during the weekdays if I'm going to order from Papa John's or Domino's. I'm just going to eat a pizza every night. I'm lazy. What's the most likely amount of times I'll be eating Domino's? Same thing. Do you see how this can be transferred? Event X could be I eat Domino's pizza. And since I'm doing it by a coin flip, it would still be a 50-50. These are all relative to a 50-50 probability. It could change and look very different if we had a different event like it's snowing or something like that. But these are all relative to 50-50, and we showed how to find the probabilities. Pretty good questions right here. Lots of interesting stuff.
Is the answer 2 or 3 or 2?
Actually, the truth is that the most likely event in the long run is 2.5. And that's the law of large numbers. So the answer to the test would be 2 or 3. It just looking at this, like for the week, and then if it said in the long run, because then we're looking at the law of large numbers, on average, how often should I eat Papa John's pizza or Domino's? In the long run. And in the long run, how often should I eat Domino's a week? If I keep doing this every week. In the long run, 2.5. Because in the long run, it will actually average out to 2.5. You can't get 2.5, because it's discrete, you can't get 2.5, but in the long run, it'll average to 2.5. And what is 50% of 5? That's why. So that's why it all works out. So cool stuff. It all kind of joins in a little bit, right? Law of large numbers playing a role again. Law of large numbers that states in the long run, if we look at this discrete event, on average in the long run with five flips of a coin, you would see heads occur 2.5% or 2.5 times. But it doesn't occur 2.5 times in one trial in the long run, because the long run probability is 50%, right? Because this is 40% heads and 60% heads, but in the long run, you'll observe 50% heads. I love it. Law of large numbers. So this is just expected values here, yada, yada, yada. We talked about expected values a little bit with this previous one. The expected value here is what? In the long run. Tell me what the expected value of this PMF is in the long run. There we go, 2.5, say it in class, perfect. In classers, everyone gets 1 extra credit. You guys are on fire today, I love it. And it's the day before spring break, love it, man. In classes, taking you to task today, onliners, we got this. The number of students that come to class, 7. You might, I don't know, well, 8. I'm sorry, person I didn't see. Where are we at? Do what? Everyone, if you email me before midnight tonight, I will give you a flat 8 extra credit. So we'll skip giving extra, I'll maybe throw up, but I'll give you a flat. So if you heard that, if you've been listening to this and you say, Brian, I got 8 extra credits today, it's not added to what you got, you just get a flat 8. Does that make sense? Everyone good with that? You accept it, you go with that. This is actually one of the best showings I've ever had for this class. So I'll do that. Okay, they convinced me. They convinced me in class. They're talking today. I love it when you guys talk. When you talk, you learn. At least when you talk in this class. So here we go. The number of people out of 10 that believe in ghosts, it really would depend where you're at. We'll follow up on that in a moment. So, these are all kind of subjective. What value do you expect for each of these in the long run? And it could be, number of sold daily at Subway in the long run could be something like at the UC 481.2. Does that make sense? In the long run, because it'll be, it can be a non-discrete number then, because it'll average out to different things. So what is expected in the very long run? That's what I want to make sure we keep understanding this. We expect to see the mean or the average. The mean right here is the mean of the population. So when we were talking about the coin flips, I keep bringing this up. It's just a way to understand it. The expected amount for that discrete event, was what? With the flipping the coin 5 times, the expected amount of heads for that discrete event was what? 2.5. Now that's confusing because that's a discrete event. But this is in the what? So much enthusiasm in class today. We are interested in the wait. Oh, hey, wait. I see something here. I'm learning. Mean, standard deviation. What's going on here? Do you see it? What do you think we're going to use? Someone say it. David M. Lane Applet, normal curve stuff, right? All of a sudden now we have a mean and standard deviation again. Now, what does the standard deviation tell us? The standard deviation is going to tell us about how spread out it is. When the standard deviation is higher, the distribution is more spread out. When the standard deviation is tighter, it's less spread out. Here's the thing. Most people, you say standard deviation, they got no idea what you're talking about. Like, hey, that's a big stats term. I don't know what it is. But standard deviation is one of the most beautiful things in the world. When I tell you your test scores were a mean of 78 and a standard deviation of 10, 68% of the class scored between what and what? 68 and 88. So, most people made C's to B's. There were very few D's and S and very few A's. Does that make sense? Now, if I told you that the mean for the test was 80 with a standard deviation of 2, what would you think then? What'd you say? Did more or less people make A's in that instance? What did we say? Careful. Yes, right there. Because I told you the mean was what? Or 80 was a standard deviation of 2. So pretty much everybody made between what and what? 99.7. Pretty much everybody made between. Yes, say it. 86 and what is that? That's 3 standard deviations. But wait, the mean was higher, but the distribution is whatter, tighter. Standard deviation is not a complicated topic. It's just how spread out it is. And then one standard deviation tells you, the typical distance 68% is plus or minus when it's normal. When it's normal, that's why we check for normality. So, when I tell you the mean was 80 with a standard deviation of 2, you're like, wow, class was really like everyone made basically the same grades. You're like, man, oh. And then you'd feel really bad if you made a 70, right? But if I told you, the mean was 80 with a standard deviation of 20, and you made a 70, how would you feel? Yeah, because then there's a lot of spread, probably due to some outliers like some large right skew. Guess I gotta go this way for right skew on the camera. But probably due to some strong outliers, then there's a lot of spread in the data. It might not be normal, who knows? But once again, standard deviation tells us how spread out it is. That's very important to us, and then we can use the normal curve. And we expect the value in standard deviation to be calculated. If one knows the probability mass function of a discrete random variable, the expected value in standard deviation of x could be computed. In most phenomena, we don't totally understand this. So here's the interesting thing, is we don't always have all the discrete events, because we could simply say here, let's look at this. What's the probability I flip 2 or 3 heads? 62, rules of probability. You can't flip 2 and 3 heads. Nice job, onliners. You can't flip 2 and 3, so they are disjoint events. We keep reinforcing this knowledge here. So they're disjoint events, and so with that in mind, we can just add them. If we say 2 or 3 events, 2 or 3 heads. So if we don't know what's going on, we will assume that we do know the probability distribution of a particular discrete random, and so we'll be able to calculate the expected value and the standard deviation. So we're saying we understand what is going on right here. We will then use this expected value and standard deviation to help us define what is unusual or rare. So let's go ahead and start looking at this, talk about some ghosts. Oh, it's so weird. You guys should see this. You can't see it on the screen. Or is it flickering green up here? Looks like the ghost has fangs. No, you'd only be able to see it up here. This is spooky. Here, wait. Does anyone want to see this real quick? It's almost like you gotta see it. Stuart, you want to up here real quick? You want to see it, Gabby? Come here real quick, Gabby. You gotta see this. I gotta see this. Start reading this stuff if you want. Gabby's gonna confirm if it looks like the ghost has fangs or I'm going crazy. Does it look like the ghost has fangs right there? No? You see it, right? Yeah. That's so weird, isn't it? It makes it creepier, doesn't it? I don't think I can see it online. Yeah, it's like a flicker on the LEDs of it, or the LCD screen. So weird. So here we go with a poll. A poll of people. A poll is a what? A what? A survey, and a survey gets you a sample. So this is not the whole population of everyone that exists. Could we have 2 separate polls? As in we could have 2 separate. Yeah. So neither one will be right. Both of them are going to be views into the possibilities. Does that make sense? It's like, well, I went out and talked to people and 65% of them said they're going to vote for me for student body president. Well, were you the one asking? Because that's going to throw a little bit of response bias there too, right? Like, hi, I'm running for student body president. Are you going to vote for me? Sure, why not? I don't even know your name, but yeah, sure. But if you do separate polls, you'll get separate answers. Do you agree that some truth exists out there for this answer? That what percent? Who in here? We won't debate it. Aliens is, I don't know. We'll do ghosts. Let's change this to aliens. I'm fixing these slides. Can I delete this? Right? We're fixing this. We're going to aliens. It's important. Will it download? Classic game of will it download? Is never going to download. Giorgio, where you at? Is not going to download. Man, well, every time, all you need to do is just imagine Giorgio. Wait, opening when complete. I don't know whatever happened to those. What happened to that? Why does that not work anymore? I love being random and throwing stuff in here. It won't. Oh, where you at, Giorgio? There you at. So there he is. So now it's all about aliens. I can't change this alien stuff, I don't think, in here, but this is about aliens. Do you believe in aliens? That's what we got going on right here. Because ghosts are probably aliens anyway, so let's go with that. Who here believes in aliens? That somewhere out there's aliens. That's depends on where. Oh, wait, oh, no aliens? You don't know right there. Anyone else aliens? So, but apparently we asked the people in the U.S. if they believe in aliens, and 40%, according to this Harris poll, said they do. Does that make sense? Then they had another poll from CBS, and 48% said they believe in aliens. Are these results weird? Are they surprising? Which one is right? Well, to know which one is right, or if they seem possible, we would actually have to know the truth. And this is something key to this chapter. Something very key to this chapter is we actually know the population. I want to make this clear. Here's the biggest thing about chapter 15. With sampling distributions, you know the truth. I can't make that clear enough about this chapter, and that's what's going to blow your minds, is you actually know the truth in this chapter. So, I mean, if I told you, I've got a big bag of M&Ms over here. Anyone like the blue M&Ms? If 30% of the M&Ms are blue in my bag, and you grab out 100 from my big trash bag of M&Ms, it's sanitary. If you grab 100 M&Ms, what percent of those M&Ms would you expect to be blue? Wow. You actually just solved something in this chapter without even knowing it. If you were to grab 100, because I told you what's true about my bag. My bag, very large bag, has what percent blue M&Ms? And it will constantly be refilled. I'll pour more in if you take some out. Like constantly, it's always going to have 30%, right? So every time you're taking from it, it's always going to have 30%. It's like a magical bag of M&Ms. Because if we were to say only 30% of people outside at UT will vote for Brian Stevens, and if you were to talk to 100 people, how many people would you expect to say they'd vote for Brian Stevens? 30 people. Does this all make sense? Now I'm going to ask it in a different way. If only 30% of people at UT would vote for Brian Stevens, sad times, what percent would you expect to say they'll vote for Brian Stevens when you go and speak to people? 30%. So if you speak to 200 people, be careful. Listen to the question carefully. If you speak to 200 people, what percent would you expect to say they'll vote for Brian Stevens? What percent? If you speak to 1,000 people, 500 people, yes. Because here's the thing. The population is what we want to understand. In this chapter, we will know the truth about the population. The sample is what we take and what we have access to. It's not really what we have access to, it's what we actually get data on. What we have access to is the what? The sample what? What we have access to get our sample from the population is our sample, review question. Sample frame. Sample frame is what we have access to in the population to get our sample from. So you might have access to the whole population, and then if you got the whole population, it would be a census. So we wished we knew the population P, proportion P, the fraction of the US adults who believe in aliens, but we only have the sample proportion P hat, pronounced P hat. This chapter will talk about the relationship between P and P hat, as well as Y bar and mu sub Y. This right here stands for the true proportion. This is an important note to take on this slide. This is the true proportion, which means the true proportion of US adults who believe in aliens. We're doing aliens instead of ghosts today. The true proportion of US adults who believe in aliens. This is taken from a what? Sample. So this would be in a sample, we found a proportion of adults who believe in ghosts, of aliens. Does that make sense? This is, we've seen mu, the true mean. Like when we say the true mean weight of US adults is 175. Does that make sense? Like all adults in the United States, like on average, if we averaged everybody out, the mean weight would be 175. So that's the truth for everybody. That's the truth. And then this is, if we go out and do what? I went out and talked to 150 adults and found a mean of this. The average of the sample. Great answer. The average of the sample. This is the proportion of the sample. I can't highlight it for some reason. This is the proportion of the sample. This is the average of the sample. This is the proportion for the population, which is the truth. This is the sample for the, I totally messed it up. This is the mean for the population. Mu is population mean. Mu, if you see Greek, it's population. Like sigma and mu go together. So sigma and mu to go together, and y bar and s go together. S is sample. So I usually say small sample statistics and Greek population. So that's what we got going on there. So we have what went on when we did our classroom free throws. We don't only do that one here because it doesn't work for the online class. But we have that people are flipping the coins. And if we have that, 3 of the ways that you can make it are where you make it. Do you remember what we had? You flip 2 coins in the simulation, and if it comes up heads, you missed the shot. Remember on the slide that showed that? And so 75% of the time people should make it. But if somebody is a 75% free throw shooter, like that's the truth. Does that make sense? If they are a 75% free throw shooter, what percent of the time should they make it on make free throws on average? If they shoot 50 free throws, what percent should they make? Percent. 75%. So let's look at what could happen here. If they shoot 50 free throws, this is all examples of 50 free throws. Do you see that sometimes they make 75? Is it weird when they make 70% out of 50 free throws? How about 80% out of 53 free throws? Over here, it starts to get more odd. But imagine if you were playing basketball against your friend. You said, I'm a 75% free throw shooter. He said, shoot 100 right now. And you're like, I got this. And you made 74. And you said, see, I told you I'm a 75% free throw shooter. He said, no, you made 74%. You're like, that's just variation. I make about 75% on average. No, you made 74. Does 74 seem believable if 75 is true? Could 74, like if I told you, there's 75% Snickers in my bag, and you got 100 candies out, you said, Brian, you're a liar. I got 74 out of 100. I'm like, no, well, it's 75%. You got a little less. I mean, there's variation. Does that make sense? In this chapter, we know that this person is a 75% free throw shooter. So what is the mean of the distribution? Where's the center at? And then what else will we need to do? Find the what? Standard deviation. And then we can talk about what we would expect if they are a 75% free throw shooter. This is where we're going with this. Lots of, way too much work on this slide. I've never liked this slide. I can't imagine anything we'd create from this. It's way too much. Well, let's look at this real quick. Imagine the population has values 1, 2, 4, 5, 7, 8, 9. We're interested in the proportion of odd numbers in a sample of 5. So we have here that the population has how many odd numbers? 1, and then we have 2, 3, 4 odd numbers. Does that make sense? And what we see here in the long run is that we have, on average, 57%. So that's probably a pretty good estimate. I've never liked this slide. It overly complicates it. It's almost like a simulation. So you got some simulation going on right here, just random samples going on. Does that make sense? Of numbers that occur. And this is actually every sequence that occurs. And so right here, the amount of odd numbers we would expect in the population of everything that occurs is 57.14. Never liked that slide. It's just too complicated, right? Too much on one slide. The sampling proportion will differ from sample to sample. Does that make sense? The sample proportion will differ from sample to sample. That means someone else comes up and they say, well, I got 77% Snickers from Brian's bag. And they're saying there's too much. Then someone else comes up and they get what? 73 Snickers. Someone else gets 75 and they say, it's exact, it's exact. But would it be weird if somebody got 40 Snickers? Well, yeah, oh, you guys are like, yes, right away. And you're right. At that point, it would be weird. But what do we need to figure out how weird something is or odd? The standard deviation. Do you get where we're going with this? Because if someone says 73 is weird, Brian, that shouldn't happen. I'd say, well, what's the probability of that or less? And that's when you go to the David M. Lane applet. So that's what we're going to do. What we're building here is a sampling distribution about the what ifs. I want to make that clear. This is all about the what ifs of what could occur when you draw from my bag of Snickers over here. I've got, well, a huge bag of candy. Candy all the time in my office. People can confirm that, right? Office candy. Can buy, get some office candy. So we got this humongous bag of candy. 75% of it is Snickers. When you draw from it, you should expect 75%. Because I told you that's the truth, right? So let's look at when we make this. Now what's going to go on is we're going to pretend one person draws 100 candies out of the bag. Then another person could draw it. And we want to talk about when something is going to be odd. So I've said this over and over and over and over and over again, that the true proportion is what we expect to see in our samples. I can't highlight all good for some reason today. Won't let me. But the true proportion, does everyone see this? The true proportion of the population is what you expect to see in your sample. This is the mean of the sampling proportion, of the sampling distribution. So we expect to see the true proportion, because I tell you, oh, there's 75% Snickers. So when you sample, what do you expect to see in your samples? That's exactly what that is. Is that the easiest thing ever? Yes. Does it make sense? That we expect to see in our samples 75%, because that's the true proportion. So once again, to read this, I would just say the mean right here, which is what we expect to see. What we expect to see in our sampling distribution is the true proportion. So what's the center of our sampling distribution? The center of our sampling distribution is the mean. See how 75% is the mean right there? Because that's what we expect to see. Now the standard deviation is the typical difference about how spread out things are. Thomas, real quick. I don't want to trip. This is where people get confused. We have to do a pause here. This is about how far out the distribution is. And to calculate that, we do P times Q over N square root. One time for me. I'll only make you do it one time. I was sick the last time we had to compete. Ooh, well, you'll lose if we compete. Be quiet if you want to find out. You ready? Online's got to say it a few times. You got to say P times Q. Oh, nice. You ready in class? You ready? You can do it as a sing song. You ready? Here we go. 1, 2, 3. P
times Q over N square root.
Compete. I don't. You guys don't want to hear. There used to be this thing called the Papa John's pizza screen, and I was used to all of that. I'm gonna break my voice. I'm recovering. You ready? I'll do it loudly. You ready? One time loudly with me. You ready? You seeing it? You reading it? You say it in your head? You got it? You ready? You can memorize it? Okay? Practice. Go. Say it.
P times Q over N square root.
You ready? 1, 2, 3. P times Q over N square root. You got to keep going, Lansing. It's one of the easiest formulas we have. What does it give us? It gives us the standard deviation for what we expect to see in our samples. So that way, when someone comes up and they get 50 Snickers and they're like, Brian, this is weird. I think someone took all the Snickers out and I think it's not 75%. Does that make sense? This is Brian, your bag is not filled to the way you said it was. You said I should see 75%. I saw 50. That's odd because it's far away. How do we figure out how far something is away? We look at how many, say it, yes, you got it. We look at how do we determine if something is far away? Standard deviation. Is a difference of 10 big? Is the difference of 30 big? I'll give you 10 more M&Ms. I'll give you 10 more cars. It depends, right? What do we need to do to any difference in statistics? We need to what it? Standardize it. Remember how we used to take a difference and divide by a standard deviation? We did observation minus mean over standard deviation. Guess what we're going to do here? We're going to take an observation minus the mean over standard deviation. Now here's an important note. The important note you must know is that for this all to work out, we need there to be at least 10 expected successes and at least 10 expected failures. So failures are the complements of successes. With my 100 selection of candy, I say, hey guys, it's the end of the semester, I got this humongous bag of candy. Come and take 100 candies. You guys earned it. How many Snickers do you expect to get out of the 100 bag? How many not Snickers do you expect to get? Does it meet the requirement of at least 10? Because 75 and 25. If I were to say, guys, I'm running out of candy here. You can only have 20 candies now. How many Snickers do you expect to get? How many not Snickers do you expect to get? Do you know what you're doing there? You are doing, and let's look at the formula. You're using P, N times P. There are 20 candies, and you expect 75% of them to be Snickers. Is that correct? That's 15. Now you could mathematically say that I expect 5 not to be Snickers. But there are 20 candies, and you expect 25% of them not to be Snickers. 5. P, NP, and NQ will add up to N, because you have the proportion that is successes and the proportion that is failures. So now you just have a number, because proportion of successes is 75, proportions of failures is 25. If you look at the number of successes and the number of failures, it is the total number. Does that make sense? NP plus NQ equals N, because NP and NQ are basically complements. P and Q are complements. So when P is 0.6, what is Q? 0.4. When P is 0.8, Q is? When P is 0.92, Q is? Nice job. Does everyone understand this concept? P and Q are complements. See how we're building off of the idea of a complement, because P and Q are just complements. Nice job on line 2. So this is what we have going on right here, is this is going to give us the spread. I can actually tell you what the spread, think about this. 75% of my candies are Snickers. 25% are not Snickers. People are selecting 100 candies, square root. There's the standard deviation, about 4%. Guess what I do to that? Times that by 2, take 75, minus it, and it would be weird if someone got about 66 or less, because that's 2 standard deviations away. That's this chapter. We're going to do more examples. I'm going to show it more in depth, but that, if you saw what I just did there and understood it all completely, you've bridged the gap between 5 and 15, and we're going to do more examples just like that. So we're going to do more with this. We're going to go back to aliens. Always back to aliens. Which one about the what? Go ahead.
Just like the middle, where it's like typically 100.
The proportion we measure is probably not equal to, yeah, like the standard. I do agree with that. It's like the how much it's typically off, or kind of like the spread, because one standard deviation is 68%, which is very close to 50. So this is kind of like most things are about within this. Does that most, because it's more than 50%, it's about 2/3, but it's not like 95%, which is where we would call things odd. But most things are within this. Like most students would get about this much, plus or minus 1 standard deviation. Does that make sense? So that's why it's kind of I do like that. That's a really good question. Who knows what we'll put on the test? But yeah, the standard deviation is 1 standard deviation is about most things. 2 standard deviations is pretty much everything. And 3 is basically everything. Because 2 is where you start to say things are odd. Like a guy my height is kind of the tallest of normal guys. I'm like kind of normal height, normal tall. Would you describe my height as that, like normal tall? But if a guy's 2 inches taller than me, all of a sudden he's tall. I'm the bridge. Like I am the 1.92 standard deviations above the mean. Once you go above my height, you are unusually tall. I like it. That's why I was born for statistics, or I grew into statistics. So do we need to worry about the size of the population when we simulate 50 free throws In theory, the average of p hat should be 75% from combined results over several sections. This is with the right here. And theoretically, this is based off theory, but check this out. What we have here is 75 times 25 divided by 50 square root. What we've done here is we've actually worked the math. But tell me this, if someone's a 75% free throw shooter, what percent of the time would you expect them to make free throws? This was done with simulation. How close is it to the right answer? Pretty close. Then to find the standard deviation of the distribution, we would do what? Say it for me one time, just one time. We would do what? I'm gonna do it with you. Here we go. Say it. Do you see me doing the formula as you say it as quick as I can? And this is the actual standard deviation, and this is a simulated. These numbers are different. Review question, how could we get the numbers better and more in sync? How could the numbers be better and closer to the truth? So what'd you say? Increase the number of trials. Did everyone hear that? That's been on the test a lot. Increase the trials, yes. Basically sample size, basically more trials. Like we've only had 330 simulations here. This is not 330 free throws. Every one of these 330s was people doing 50 simulations. Does that make sense? But if we did more, then the law of large numbers states that in the case that it's truly 75%, it should get closer. It's gonna like weave in closer to it. And this is truly this right here. The simulation is not perfect, but if we increase the amount of trials, we'll see closer to the truth. Law of large numbers, simulation used right here. Review stuff all the time. So here we are. Let's go back to it. We just did it right here and we saw the answer to the question. P times Q over N square root is equal to 0.06123, which is very close. We didn't do something wrong here. I've already jumped the gun on this answer. We did nothing wrong. And that's usually I have the slides open on the left, so I can be like, oh, it already does this example because it's so key. We didn't do anything at all wrong. We can increase the trials to get a more accurate result. So a more accurate results closer to the truth. So let's look at this in practice right here. This is what we want. This is a key slide. This is the aggregate of everything you've learned so far. That when we know the probability mass function and we understand the probability of the event, we could then use that probability and say that when we sample, what would we expect to see? We'd expect to see when we sample, right here, when we sample, what would we expect to see? The true proportion. Yeah, I mean, I'm telling you, 60% of people are big UT fans here. The rest aren't, 40% aren't. So you go out and talk to people around campus, what would you expect to see? 60%. And then how much would that vary? It would vary by, the spread of it would be by P times Q over N square root. That's really helpful. But will it always be normal? Can you always use that normal curve? Can you always just say, oh, it's gonna be normal. I can do the empirical rule. It's only normal if there's at least what? 10 successes and 10 failures. That's what this says right here. I already told you guys these formulas, NP, NQ, greater than or equal to 10. At least 10. If it's exactly 10, that's fine. We don't try to throw tricky stuff on the test like that. But think about this. Okay, I'm gonna go out and talk to 30 students. Does that meet the condition for normality? Think about it. I'm gonna talk to 30 students with 60% being UT fans here on campus. You can cheat and use the calculator if you want. How many successes, how many failures? You're right, nice job. Because I said there's 60% UT fanatics. I'm making up these numbers. I'm pretending I know that 60% of UT fans are fanatics. And 30, that's 18, and 12 is the other one because this is this. But you could confirm, do 30, we'll do 40% times, and there we are 12. So we have confirmed that now, what does it mean that we meet this condition? It will look what? What does this stand for? Normal. You guys remember when we used to do normal with a mean and standard deviation? Nice job. So with a normal with a mean and standard deviation, we see that normally distributed with a mean of the true proportion and a standard deviation of p times q over n square root. And this means the sampling distribution of the sample proportion will be normally distributed with a mean of the true proportion and a standard deviation of p times q over n square root. This is how it'll look. This is how it'll look. What do you notice? 68, 95, 99.7. 68, 95, 99.7. Love it, right? If you know chapter 5, you're good. If you don't know it, time to review. Time to practice chapter 5. Look at this again. It's like they're twins, right? I mean, not perfectly, but it's all right. This is what we could have had theoretically. I kept solving this right here. It's no longer on my calculator, but this is theoretically what we should see. So theoretically, this right here, and look at this. Do you see where the 60 mark is, where the tail starts to go? Do you see where the 90 mark is, where the tail starts to go? Do you see where the 60 mark is, where the tail starts to go? Do you see where the 90 mark is? Now the bin widths make it look a little bit weird, but do you see how it basically ends here and basically ends here? And guess what? Basically ends here, basically ends here. Pretty good, right? Pretty good. So now let's look at some aliens. Just aliens here. I'm trying to do the aliens hands. So when we look at aliens, we find out that 45% of people actually believe in aliens. 45%, a little bit low these days. So how would we, we go out and talk to people, what would we expect? What'd you say? Go ahead, knew you had it. Wow, just like right like that. I was like, you got it right away. Because I told you, in the population, what percent of people believe in aliens? So if you talk to people, what would you expect to see? In a sample. This is what you are literally doing, is you're saying, I'm gonna go out and talk to how many people? We talked to a lot of people today. Talk to them about aliens. And now, what is like the spread we expect to see? Like how spread out should this distribution be? We should expect a spread of p times q over n square root right here. Does that make sense? And guess what we do to this graphically? We put the mean at the center, and then you go up 1 standard deviation, you go up 2 standard deviations, you go up 3 standard deviations. Then you go down 1 standard deviation, you go down 1 standard deviation, you go down 2 standard deviations, and you go down 3 standard deviations. Does that make sense? Was it odd what we observed here in our sample? Oh my gosh, that's so many. Something's different here. No. What percent of the time would this occur right here or higher? Use the empirical rule. Between what and what? Careful. What percent of the time would this or higher occur? So we're talking about the area under the curve over there. Yes, that or higher. You are right. Because how many, just look at them down here, how many standard deviations am I above right here? How many standard deviations is this above the curve? So what is in between here and here? Say it with me, how much? How much is outside? What's one of my hands worth? Do you see that? And then right here, how many standard deviations are we above the curve? 2, so what's -2 + 2? 68, 95, and then what's on the outside of 95? What's one of my hands worth? 2.5. Do you see how that's 2.5 right there? So somewhere between 2.5 and 16%. So that's not really our criteria of above 2 standard deviations as denoted right here. That's not really super odd. I mean, it's a little high. I mean, but you know, you get a little high, a little low. Let it go. That's still our standard of like, that's pretty odd right there. Like that's 2, because 2 relates to, we haven't gotten to that yet. So the margin of error. So we have 68, 95, 99.7. So what we have right here, the margin of error is generally taken from 2 sigma limits. And in this case, 2 times 1.75 is equal to 3.5 percentage points. And you see here, if you go from right here to right here, what's that difference? 3.5%. Does that make sense? So we see that this is within it right here. If I were to say 95% of the time when I go out and do polls, what would I expect between what and what? Between that and that. Does that make sense? If I were to go out and do samples, like let's say I have a big bag of candy, and I'm gonna have you take 808 pieces out of it. Then 95% of the time, the proportion of Snickers you get, if the proportion is 45%, would be contained in the interval what and what when you sample that bag. If you take 808 candies, 95% of the time you would see what to what. Yeah, just that. And what would you expect? Yeah, that's it. Remember, this is from sampling from a population. That's what the hardest thing for people to get about this. You're actually going out and doing samples. You're saying, well, 95% of the time when we do a sample, if from 808, we should see this if the truth is 45. Does that make sense? We know the truth. Like apparently the truth is 45, and with that known, here's what we should see 95% of the time. Could we get something weird up here? Is this possible? Is it probable? Yes, that's exactly right. It's possible, but not probable. So we could z-score it and look at this. What did we observe in our sample? What did we expect? Then what was our standard deviation? What do you see? Observation minus mean over standard deviation. Does that make sense? When you look at that 1.17, it literally means it is 1.1 standard deviations above the mean. Draw it out again for this chapter. This is 1.71 standard deviations above the mean, which is not too unusual. It's a little high, right? It's like me. This is the Brian sample. You're like, that's a little high. Not too high, but a little high. So we can say our measured 48% is just 48%, 45%. It's like, yeah, I mean, that 48% is just like, it's like when someone gets 78 candies out of my bag, I'd be like, yeah, well, it's a little high, and not too high. We can actually figure out from my bag what a little bit high is. Let's do that. I think we've got the switch over now. We're good enough to do this. Watch this. Here's how easy these questions are. I say easy, but you have to know the tricks. One, let's go ahead and say Brian has a big bag of candy that will be constantly refilled every time people take candy out. It will constantly have 75% Snickers in it. No one can steal the Snickers from it, and you're not allowed to take candy such that you see what you're getting. You just take a big scoop, or it's like a machine that you pull a hook and it just puts candy in your bag. You get 100 candies every time. And they're kind of mixed up, but it's 75% Snickers. You understand what's going on? So at all times, the amount of Snickers in this population is what? 75%. So what would you expect? Does that make sense? I'm putting this in as a placeholder right now to make it not look weird. And it always looks weird. There we go. That's just a placeholder. And I don't want a placeholder anymore. What is the standard deviation? Ooh, P times Q. It's easy formula, right? P times Q, which they're complements of each other, over N, square root. And guess what? Copy, paste, done, delete decimals so it appears. Not the first time we've done that. With 100 candies in the bag, how many Snickers would it be weird if I was like, oh wait, you did something weird here. It seems to me like you rigged it. You got too many Snickers. 84. That's the first actual discrete event after 83.7. And so I think that'd be a great answer on the test. I would totally accept that. 84 is weird. And how did we figure out what was weird? We said, what do we expect? And then what is the deviation around that? Does that make sense? Because if people keep coming up to my thing, this is why it's a sampling distribution. I'm really trying to hit this home today. It's a sampling distribution because there is a truth for what you should get, right? And then everyone is coming up and getting 100 Snickers or 100 candies. Does that make sense? So this is what we think will happen. And not what we think. It is what should happen mathematically if everyone's getting a random sample. And that's important. It's random. No one's going through and taking things out. Everyone's getting a random sample. Now, should this be normal? Should it? I don't know. Well, I mean, how many Snickers do I expect to get again? How many not Snickers do I expect to get? So is it normal? It is. It's good enough to be normal. 100 times 70, oops, I messed this up completely today. 0.75, 100 times 0.75 is that, and 100 times 0.25 is this. So I expect 75 Snickers, I expect 25 not Snickers. We're gonna finish up the last few bits of notes on this. This is just, we're going slowly. How good is the normal model? The normal model is a better approximation for the shape if we have a large sample size. So, and this is key here, we need at least 10 successes and at least 10 failures, and then it's approximately normal. We have 3 conditions we've been talking about here, and the second one I really don't care for. Do not ever say to me again, QQ straight enough, no outliers, plot doesn't thicken. Erase that from your head. Never say it. I will fail you in the course if you say that from now on. I can't, unless we're being, I won't fail you. But unless we're being super tricky, I can't imagine. We've never thrown like old review questions. The final exam does have 2 questions that are meant to be like, do you remember how to use the techniques? They're not rote memory questions. They're like, someone wants to go out and do a study of the differences between the satisfaction at KFC and McDonald's. They have people fill out a survey card at both restaurants, and then they figure out if there is a difference between the ratings. What would you use? So it's not a rote memorization, it's understanding, do you understand what you've learned in the course? It's not QQ straight enough, no outliers. So you can toss that out of your brain. From now on, when I say, condition 1, what do you say? I will say it like that a lot. You say what? All you have to say is random. You say random. Say random. And break this one down to something shorter. Condition 2, that's all you say. Condition 3, here's the thing. You pause. You must pause every time. Condition 3 will change. Condition 1, random. What does that mean? It means we don't have someone going through and saying, hey, Brian, I got 95% Snickers. And they're like, I just took what I wanted. Like, well, that doesn't meet our condition that if it's randomly selected. So of course you got that. You cheated the system, right? So you need to randomly talk to people. I don't, if I'm talking to people who might vote for Brian, well, I'm talking to alien people, I don't go to an alien convention, and everyone's like, I believe in aliens. Like, that's not a random sample of the population. You need to randomly sample the population. You can't cheat and pick things out, or you can't go to a spot that is not representative of your population. So a random sample literally means, or randomization condition literally means that you took a random sample from the population. 10% condition. I ask that you just believe me. If you would like, you may read this article. This is the wrong one. I think it's the next one. This is the one. If you want to understand why we do not sample more than 10% and why it leads to more error in finite populations, you may read this. This is the error that accumulates after 10%, which is small. This is the error that accumulates after 15%, which is more than double of that. At 20%, it's about 5 times bigger. And if you get towards 50%, it's 20 times bigger. This means the percent, and you can read this article on it if you want. So there is an article, gets into the whole theory. A puzzling rule. A common question about the assumptions for inference in AP statistics is, why is there attached to a certain inference that we sample less than 10% of the population? Why is it less than? Once again, you may read the article or you may believe me. We don't need, you just want to believe me? So when I say 10% condition, what are we going to say? That we have sampled what? Less than 10, no larger than 10%, same thing. Less than 10%. So I'm going to go out and talk to UT students. I'm going to talk to 20,000 students and ask them if they're going to vote for Brian. Did I violate any conditions? Because we don't have how many students are at UT. You're exactly right, 200,000. That'd be a great answer on the test. We have violated the 10% condition because there's not 200,000 students on campus, so sampling 20,000 would be more than 10%. You could even do the math and say, if it said there are 30,000 students here at UT and Brian samples 20,000, Brian sampled 66%. You do not need to explain this adds error into the calculation for finite populations. Do the AP statistics article. You don't need to get into that. It's just that this violates a condition for the mathematics. You can look at the article, you can understand. All these things have been thoroughly researched and theorems and everything have been done through them to show the mathematics for it. But if you want to just believe me, which you're free to do not sample more than 10%, and that will follow. All these conditions will follow for what we're doing in all chapters to remain. We will do random, we will do 10%. For this chapter and 2 other tests / interval we will have the success failure condition. The success failure condition is based on categorical data. When I ask you, do you believe in aliens? I'm asking you what type of question. When I ask you, did you get a Snickers, or not how many Snickers, did you get a Snickers? Because we have to look at each candy and say Snickers, Snickers. Each one of those observations is a what? Is a categorical. Kind of a discrete event. It's a discrete event. Exactly right, too. Discrete events, categorical, and discrete events. Like, it's discrete event of this. So we have right here categorical data. Does that make sense? So with this in mind, when we do categorical, like, do you believe in ghosts? Or did you get Snickers? Like, I got a Snickers, I got a Snickers. You're literally looking at each one. Snickers, Snickers, talking to each person. Do you believe in a ghost? Do you believe in aliens, ghosts, whatever? This is categorical. And what have we said we need for normality here? We need what? 10 successes and 10 failures. That's why I kept saying successes and failures, because it's a success-failure condition. It is the success-failure condition. And if we meet all the conditions, the distribution will be what? Approximately normal. And you could just say normal, approximately normal, good enough to use the normal. And why do we like using the normal? Because what do we have? We have 2 things. Go ahead. David M. Lane applet, and we have the empirical rule. So that's why we want to do it. We want to meet these conditions to use our 68, 95, 99.7 rule. And watch this. Of all cars on the interstate, 80% are said to be speeding. Do we meet the condition of at least 10? 80% of 50 is what? That is, it's 40. 20% of 50 is what? If one's 40, the other is 10. Do we meet the condition of at least 10? Is 50 cars on the interstate less than 10% of all cars that are on the interstate at like all times at ever? Yes, there's more than 500 cars that have ever gone on the interstate. So with this in mind right here, let's look at this. Let's go ahead and figure out if we expect 80% of cars to be speeding on the interstate. There is a small problem with this. I don't want to point it out right now. What would we expect to see in the next 50 cars if we expect 80% of cars to be speeding on the interstate? How do I figure out the spread of this distribution? And this tells me, if I go out and sample 50 cars, here's what I expect to see. What would be an odd amount of cars to see speeding? 92, 91. 91 is just a little bit lower, but around 92, 91. Does everyone see that? Because that's 2 standard deviations. 52% of people plan to vote. So you don't know it, but 52% of people plan to vote yes. This is like one of your questions. We'll end with this one. So we're going to talk to 300 people. P times N is 156. Q times N is 144. Believe me. I'm not quoting anybody there. Oh, God. So that's what we expect, right? What am I doing now? I'm finding the what of the distribution. So if we go out and sample, like the truth for this resolution is this, the standard deviation. Nice. This is what will happen on election day. 52% will vote yes. What percent of the time when we go out and sample would we see less than 50%? Look at this. Is it quite possible that in a sample we could see less than 50%? Because look where 50% is at. The z-score for 50% is very close to 0.6. Do you see it's right about here? I'm going to put a mark for the in-classers right about there. And watch this. I go to below. What's the probability of seeing it fail? I was a little off today. Right there. It's right there. So in 24.4% of samples, we would say the resolution fails. Imagine if we just went out and did one sample. Does it seem quite possible to be like, oh, the resolution looks like it's going to fail? But the truth is 52%, right? But with the truth being 52%, is it possible to see 50 or below? Yes, and we know that by the spread. What is the z-score of this? Well, we take observation of 50 minus mean of 52. It's negative, obviously. We divide by standard deviation, and it's a z-score of negative 0.7. I should have been better with my mental math because I said 0.6. I was probably close when I did that, but it's negative 0.7, which means, rounding it, it falls a less than 1 standard deviation below the mean or 0.7 standard deviations below the mean. Look at this right here. That's what it is. It's 0.7 standard deviations below the mean. Is that odd to see? This would occur between 16 to 50% of the time. You guys are good to go. 1 minute late. Sorry about that. And you guys are good to go. Does this chapter kind of make sense so far? Do you see how it's a build on chapter 5? Do you understand conceptually what you're doing by going out and taking samples where you know the truth? Yes, that's the key. It's a conceptual thing you have to understand about this. People get these questions on the test, they're like, what is this question? You're welcome, Garrett. So just keep going over these examples. We did a lot of examples today. We'll do the second part of this when we come back, and it deals with memes. It's the same thing. It's what we did last time with the porch stuff, because you're saying if you invite a random group of friends over, guess what condition 1 is next time? Say it for me. Random. Guess what condition 2 is? Don't do a condition 3 yet. Condition 3 is nearly normal, which we haven't gotten to yet. It's for quantitative data. So we haven't gotten to it. Hey! That's all right. Split 1, split 2, split 3. Your first split is weekly. See, it's languages. So these are people who speak 1 language, 2 language, 3 language, and 6 languages is discrete data. So weekly money spent outside a meal plan. These people spend less outside a meal plan. These people spend more. Do you think international students are more likely to live off campus? Do you think international students are more likely to speak more languages? So maybe the people speaking more languages, you see, because these people speak more languages and they spend a lot of money outside meal plan. Maybe they're older students who are international or something like that. And so that's what I would think from this, because they spend more money outside of meal plan. And what do you see between the association here? The association is what? Positive. Project due at midnight. Project due at midnight. Association positive because the more money they spend outside meal plan, the more languages they speak. Yeah, this is people speaking 1 language, 2 languages, 3 languages, 4 languages, 6, and then it's dividing it.
It's fine. I just didn't know like all of this junk. If that was like.
You see how this is very small right here? Yeah. That's your 25 people, and these groups are slightly larger. That's a lot.
Okay.
Good job. What's up, Stuart?
The third condition,
Success failure?
Yeah, is that when we check to see if it's categorical?
You won't check, well, yes. To do that condition, you need to check to see if it's categorical. So yes, when you get to the third condition, because the next time it'll be like, you plan to invite a random group of 20 friends to your party, and you don't want your balcony to break. What is the probability it breaks if the mean for the population is yada, 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 yada. And with that, it would be weight, which is a quantitative variable, and if it's quantitative, it'll be the nearly normal condition. So if it's categorical, like the question being asked, always go that, like, do you believe in ghosts is categorical. Well, people get confused because they say, well, we're saying we expect this many people to believe in ghosts, and we're using the normal curve. Just go to the question. The question was, do you believe in ghosts? And then over here, when you take your sample of 100, you'd have to say, did I get a Snickers? Did I get a Snickers? And you would sample it that way.
Because that's like on the test I just did. It's like list all QQ shared number outliers.
Yeah.
And then don't fit.
Yeah.
It's like list that out and explain them. So
yeah.
What I need to explain, it is categorical.
No, the explanation for that one, you'll see on practice test too. The explanation for that one is for success failure, you do NP equals blank, NQ equals blank, and then you would say both are greater than 10.
All right.
Yeah. So yeah, basically by saying NP, NQ and solving for them, you're saying there are 10 successes and 10 failures. And so that's the big thing, like NP was this, NQ was this, and they are both greater than 10. Wait, you are viewing pod user screen. Yay, good job.
That helps a lot.
Awesome. End the meeting.